Example 6. Use a vector projection to find a force. A 10,000-pound boulder sits on a mountain at an incline of 60 degrees. Ignoring the force of friction, what force is required to keep the boulder from rolling down the mountain? So basically, if you look at the picture, here's what we're trying to establish. If a person were to be here on the mountain and they wanted to hold up this rock or this boulder, how much force would they have to be able to exert to keep it from rolling on them? Now, a lot of people would just guess. They're like, oh, it's 10,000 pounds. You'd have to have 10,000 pounds of force. Well, that's not exactly right. The 10,000 pounds is a force of gravity, which pulls it straight down. So this vector here, you could represent as 0, then negative 10,000, because gravity pulls straight down. But the fact is, it would be rolling down this mountain, which has an incline of 60 degrees, which means it would not roll down with all this force. Some of it would be limited. The way mathematically to figure this out is a projection. You're taking the weight and we're going to project it on this vector here. Now here's how we solve this. Rather than going into a big projection like we just did in examples 4 and 5, we can project this onto a unit vector. A unit vector would represent something that's like this direction, but we just have a value of 1. It makes things a lot easier to work with. So let's start with what we know. If we're going to project this over here, what we know about this vector. Well, it would come down and hit 60 degrees down here, but that angle would be on the tip. So usually a unit vector, let me write this down. A unit vector has a length of 1, or a hypotenuse of 1. It has an h of 1, because that's its magnitude. That's the definition of a unit vector. That's why we call it that. It has an h of 1. And so normally also, when we find a vector, we would have h cosine theta to find our x, and h sine of theta to find our y. Because our h is 1, we would say, and in this problem, our theta is 60. We could say 1 cosine 60 and 1 sine of 60, except for one thing's different. Because this tip will be touching down here, the angle would be on the tip, which means we need to flip the arrow, which means our hypotenuse would flip and become negative. So we're actually going to treat this as being negative 1 cosine of 60 degrees and negative 1 sine of 60 degrees. Now that's what we're going to project this to. So from the previous problems, if I want to find a projection of the force onto this vector W1, the way I would do so is I would dot U dot F with U dot 1, excuse me, W1 over, and then I would do the magnitude of the W1 and square that magnitude. And then we would multiply that times W1. Now let's see how this simplifies the problem using a unit vector. The force, that's this vector here, that would be 0, negative 10,000. And that would multiply times, or it would dot with W1. Well, W1, we just said we're going to treat as a unit vector, and we got this value here. Now, I'm going to simplify this by using the hand trick. We know 60 degrees is our pointer finger. So if you're looking at your hand, point your finger, you take it, you bend your finger, flip your hand over, and you would get, for cosine, I would have one finger, so it'd be square root of 1 over 2, and then over here I would have square root of 3 over 2. So now, how does that simplify? Well, negative 1 times 1 is negative 1/2. And then over here, I would have negative square root of 3 over 2. I'm going to do a dot product between these values. So we take our x times our x, which is 0, and I add it to this. And it would be negative times a negative, which is positive. And this 10,000 divided by 2 would be 5,000 square root of 3. So that's the dot product there. When we combine those together, you'll get this. We need to divide it by the magnitude squared of W1. Well, W1 was a unit vector. That was over here. This, by the way, is W1. Oops, should have put it over here. And so the magnitude is 1 because it is a unit vector. So it's just 1 squared, which is simply 1. So we take this and we divide it by 1. So now we got that to find the projection of the F on the W1, you take this and you would multiply that value times W1. And actually, before I continue too much further, this right here is the force that's required. What I would now, when I dot it together, it would get the X amount of force I need to put out and the Y amount of force. So we have the projection, it's this divided by this, so it'd be this number here divided by 1. And so let me just write that out clearly so we have it down, that F dot W1 over the magnitude of W1 squared is equal to 5,000 square root of 3. That's where we get that value. That was 1. This up here was 5,000 square root of 3. So that's where we got that. That's actually the force right there. The direction, so that's what it's asking for. So honestly, this is our answer here. But if we wanted to know how much directional force you'd have to put out, the directional force you would find by then taking that value of the force and you would multiply by the unit vector. So I'll take that 5,000 square root of 3 and I would dot it with W1, which W1 we have up there as, when we simplified it, be negative 1/2 and negative square root of 3 over 2. And so this would be the directional force of the rock. And so if I really wanted to know how much to hold it up, I would take the positives because I would be pushing to the right and up. But this is the directional force of the object falling. You would take and you would just multiply those out. That's how you would do that. So we would have negative 2,500 square root of 3, and here we have negative 2,500, and then we times that, the square roots we cancel times 3, so it'd be negative 7,500 like that. And this would be the directional angle of force. But this is what I'd be looking for right there. So here's the simplified way of doing all this. If you have to do a projection, you take the gravity and you just multiply it with the unit vector, and that'll give you your value. Now try this one, and to kind of simplify it again, take your directional force, which in this case is going to be 0, negative 5,000, and I want you to dot that with the unit vector here. And I notice it's going the opposite direction, so the unit vector, this one will be negative again because we're switching directions. This tip would come down here and the angle's touching the tip, so you'd flip it around. And so you're going to do a dot product, dot product with negative 1 cosine of 15 degrees and negative 1 sine of 15 degrees. If you do that, you should be able to get the right answer.